Hello, this is Dr. Jennifer Ribble here to talk about Chapter 1, which is on matter and measurement. We start off Chapter 1 talking about what is chemistry. So chemistry as a field is really the study of matter. So it's about what are things composed of, how do they interact with other things, what are their properties, how does it interact with other pieces of matter. When we're talking about matter, we're talking about anything that has mass and takes up volume, whether those things are naturally occurring or man-made things, from pharmaceuticals to the foods we eat to the personal care products that we use. All of these things are matter. And so how I like to remember this is I matter, you matter, everything is matter. There's different states of matter. So there's the solid state, and a solid state really has a definite volume. It maintains its shape regardless of the container, and the particles lie close together in a regular pattern. And so what that means is if I have something that is a solid and I go to put it into a new container, it's going to maintain its shape. It's not going to kind of conform to the shape of its container. And so we can look here, these are all depictions of salt, and you can see that salt is really composed of sodium and chlorine in that top left picture, and you can see that that structure is pretty rigid. Those atoms are going to come together in a very predictable way. They're not really going to move like past each other. The particles are moving, but they're not really flowing past one another, and you can see that in that solid structure of salt. When we're talking about the liquid state, liquid has a definite volume, so just like solid, you can say something, I don't know, takes up 4 centimeters cubed, for example. The liquid state, you can also define that volume. So I can measure out, say, 4 milliliters of water or oil, whatever that liquid might be. The difference, though, is that it starts to take the shape of its container. So if I pour water into a container, it's not going to, stay in that nice stream that I poured it into the new container from. It's going to really take the shape of its container. And so if I pour water into a beaker, it's going to take the shape of that beaker. Or if I pour it into a test tube, it'll take the shape of that test tube. Within a liquid, the particles are still close together, but at that point they can start to kind of slide past one another. And so you get kind of that flow and that movement within liquids. So these are just some examples of liquids. You can see, again, they're taking the shape of that container, but you can still define how much volume there is. When it gets to gases, gases don't have definite shape or definite volume. So both of those things are going to depend on the container that you're putting the gas into, or you're collecting the gas in. If you have a very large area, then your gas is going to kind of move to take up that entire area. Whereas if you have a small area, that same amount of gas can occupy a small area. Within a gas particle, the particles are much further apart, and they start to move around randomly. So where in a solid, they were kind of tightly packed, they had that definite shape. In a liquid, you started to get particles moving and sliding past one another. Within a gas, those particles start to kind of escape the attractive forces between one another, and they start to kind of fly all over the container. And so you get no definite shape, no definite volume in that random kind of movement. So you can just see some examples of gases here. So just to kind of summarize the states of matter, and I know you talked about these with Dr. Smith when she so graciously filled in for me, but just to summarize, a gas is going to take whatever shape and volume of its container, and it's also going to be compressible, which just means I can take the container that it's in and shrink it down, and I'll be able to do that. A liquid is going to take the shape of its container, but it has a definite volume. I can pour it out into, say, a graduated cylinder and measure how much of that liquid I have, but I can't compress it. A solid is going to have that definite shape and definite volume, and again, I won't be able to compress. Within when we're talking about matter, all matter has physical properties. These are properties that can be observed or measured without changing the composition of the material. So we're talking about things like boiling point, melting point, solubility. Does it have a smell? Is it a solid at room temperature, a liquid at room temperature? What color is it? All of these things are properties that we can observe without changing the composition of the compound itself. And so these are just some examples. Is it soluble? Meaning, does it dissolve in water? What is its boiling point? What is its melting point? When I am looking at the melting point and boiling point of, say, water, in order to measure those, I'm not changing it so that it's a different substance from water. It's still water. I'm just taking it and moving it through different states. What mass it is, what shape it is, these are all physical properties. I can measure them without changing the identity of the substance that I'm looking at. When I start to change things physically, we call that a physical change. So I'm altering it without changing the composition. We're going to cover those more in Chapter 7, but one example of a physical change is just changing the state of something. And so if I take solid water, I add heat to it, it goes through melting and becomes liquid. I can continue adding heat, and eventually it'll boil and turn into a water vapor, but all the while it's still water. And so that indicates a physical change. So this is just a depiction of what happens when water turns into ice. So you can see as these particles are kind of starting to freeze into that crystalline structure, the molecules themselves are still water molecules. They're still the same identity. It's just they're changing their structure in relationship to one another. So on the flip side, we have chemical properties and chemical changes. So when we're talking about physical changes and physical properties, we're talking about substances remaining the same. They're the same identity. When we're talking about chemical properties and chemical changes, we're talking about substances converting into another substance. So we're really talking about how things react with other things. Chemical changes and chemical properties we'll discuss more in chapters 5 and 6, but just to give you an introduction, these are situations where you are changing the identity of that substance. And so we look at things like flammability, does it burn, its oxidation state, and some of these things, we haven't gone into, and that's okay. But, is it stable? Is it explosive? Is it toxic? How quickly and how violently does it react? These are all chemical properties that we can look at. So this right here is just a reaction of sodium and potassium in water. So sodium and potassium are both metals. We're pretty familiar with sodium and potassium. But they are actually reactive with water. And so when you store pure sodium or pure potassium, you actually have to store it in oil so that it doesn't react with the moisture in the air. But this is just sodium and potassium being put into water, and you can see that it undergoes chemical change here. Then we can say that one of the chemical properties of sodium and potassium metal are that they're reactive with water. So matter can be classified in a variety of ways. You can classify something as either a pure substance or a mixture. With pure substances, you're only looking at one single component. So that would either be an atom or a molecule, depending on if you're talking about a single element or if you're talking about that element combining with other elements to form a molecule. So when we're talking about atoms, we're talking about just a single element on the periodic table. So we might say oxygen or carbon. Those are elements, and when we're talking about elements, a single unit of an element is called an atom. Now, when you start to put those elements together, you form molecules. So, for instance, when you put two hydrogens and an oxygen together, those different atoms combine to form a molecule of water. And so these are both pure substances. There's constant composition, regardless of the sample size or the origin of the sample. If I take a sample of pure water from one location and a sample of pure water from another location, that composition is going to be the same, no matter if I take a drop or a whole swimming pool full. You can't break these down into other pure substances by physical change. That just means that these are in their purest form. On the flip side of that, you have mixtures, and mixtures are composed of more than one component. So, for instance, if I take salt and I dissolve it in water, that's a mixture. They can have various composition. It could be solids mixed with other solids, or liquids or gases. And then you can separate those by physical processes. So maybe you use their densities to separate them, or you use solubility in water, which is a physical property. You can use those properties to separate mixtures, whereas when you're talking about atoms or molecules, which are pure substances, you can't separate those by physical processes. So when we're looking at mixtures, sugar dissolved in water is a mixture. You have the sugar molecules, you have the water molecules, and so that's your mixture. So we already talked a bit about elements and compounds. Again, elements can't be broken down, and a compound is a pure substance found by chemically joining two or more elements. So again, we talked about hydrogen and oxygen combining to form water. Various different elements and compounds. Aluminum foil, you're looking at just a single type of atom here. And you can see that these are all the same. Each one of these is a single aluminum atom. And so we would say that this is a element here. Nitrogen. Nitrogen is a gas. It is elemental. It's just nitrogen. Water, on the other hand, we have hydrogen and oxygen combining, and so this is a compound. And then salt, we looked at a little bit earlier. That is another example of a compound. So when you're classifying matter, you can ask yourselves a series of questions to determine, how do I classify this piece of matter? So the first question you would ask yourself is, can it be separated by a physical process? If the answer is yes, I can separate it by a physical process, then we know that it's a mixture, because it can be broken down and separated. However, if it can't be broken down, then we say it's a pure substance. And then you want to ask yourself, can that pure substance be broken down into simpler substances by a chemical reaction? If the answer is yes, then you have a compound. So, for instance, water has hydrogen and oxygen. You can use a chemical process to break those elements apart from the compound. On the other hand, if it can't be broken down, so we saw that sample of aluminum, if I break that down, all I'm doing is taking a smaller sample of aluminum. So I'm not actually changing the substance. So we would then call that an element. Okay, so I think that is about as far as you got with Dr. Smith. So, significant figures. Significant figures is one of those concepts that takes a little bit of time and a little bit of working with them in order to fully understand the concept. And so don't worry if you are finding yourself a little bit confused with them at first. They continue to pop up throughout the semester. So I think it's good that we kind of learn them now, focus on them now, and then continue using these principles throughout the semester. But yeah, significant figures is basically a way to let people know the precision of the instrument that you're using. So for instance, if I go to the doctor's office and I step on a scale, they're going to give me a mass that goes to a certain number of decimal places. So say they can give me my mass to the hundredths decimal place. Okay. I can't then go to somebody and tell them my mass to 10 decimal places because I wasn't told that information. At that point, you're just making up numbers, right? Okay, yes. So at that point, you're just kind of making up numbers. And so what significant figures does is it tells people how precise your instrument actually was, so that they know what numbers are meaningful and at what point the numbers no longer have an appropriate meaning. And so, yeah, let's start out with talking about an exact number versus an inexact number. An exact number is a number that's going to result from either counting objects or it's part of a definition. So, for instance, I can say I have 10 fingers. I have 10 toes. I can say that 1 meter equals 100 centimeters because that's a definition. I can go to the store and order 12 bagels, whatever it might be. And because that's an exact number, an exact number does not contribute to the number of significant figures, or I should say it does not limit the number of significant figures that you're allowed, because it's an exact number. Inexact numbers are going to result from measurement or observations, and there's going to be some amount of uncertainty. So if I take a ruler and I measure something in centimeters, and my ruler has tick marks for centimeters, and then also it has tick marks for millimeters. So, it's broken down further. There's a limit to how many decimal points I can provide, right? I can't say I have 15.679437 centimeters because my ruler is not precise enough to measure out that far. And so when I'm measuring something, I can only be as precise as my instrument allows me to be. And so that's where significant figures comes in. So determine significant figures, there's quite a few rules that you have to follow. But again, the more you use them and the more you think through significant figures, the easier this ends up being. So the first rule is all non-zero digits are always significant. If you see something that is not a zero, then you know that it is significant. So in 65.2, we have 3 significant figures. In 255.345, we have 6 significant figures. Any non-zero digit is always significant. And then we have our rules for zeros. A zero counts as significant when it occurs between 2 non-zero digits. So if we have 2 non-zero digits and zeros in between, any zero that is sandwiched in between is automatically considered significant. So when I'm looking at 29.05, the 2, the 9, and the 5 are significant because those are non-zero numbers. And that 0 is sandwiched in between the 9 and the 5, so that is counted as significant. That 29.05 then has 4 significant figures. When I look at the other example, I have 1.0087 milliliters. The 1, the 8, and the 7 are non-zero numbers, so they're automatically significant. And those 2 zeros are sandwiched in between non-zero digits, and so those are also significant. So there's 5 significant figures in that. When you look at that next point, a 0 is counting as significant if it ends at the end of a number with a decimal place. So what we call this is a trailing 0 after the decimal place. So a trailing 0 after the decimal place is significant. And so in that first example, we have 3.7500 centimeters. There's 5 significant figures there because the 3, the 7, and the 5 are automatically significant because they're non-zero digits, and then the 2 zeros are trailing after the decimal place, and so there's 5 significant figures there. This other example is a little bit tricky because this 0 is an example of a 0 that's before a decimal place that is considered significant. The decimal place after the 0 makes that 0 significant. This rule is a little bit trickier, and it's one that we will. It almost seems like an exception to the rule, and so as those cases come up, we can continue to work through those. But if you have a decimal place after a trailing 0, that decimal place is going to indicate that those trailing zeros are significant. A 0 does not count as significant when it occurs at the beginning of a number. So in this case, we have zeros after the decimal place, but there is no non-zero digit before the decimal place. So we can't say that they're sandwiched because there's no non-zero digit before them. So all those zeros are really just placeholders and are not significant. So in 0.00245, we have 3 significant figures. In 0.008, again, those zeros come before and are not significant, so there's only 1 significant figure there. Zeros are also not significant if they occur at the end of a number that doesn't have a decimal place. So in this 2,570 meters, there is no decimal place, and so that trailing 0 is not significant. The same is true in that second example there. So we have 3 significant figures and then 5 significant figures there. Okay, so this chart just really sums up those rules that we saw. And so when we're doing these examples, our first rule is a number is a significant figure if it is a non-zero digit. So we're looking at 4.5, the 4 and the 5 are both non-zero numbers, and so we would say that both of those are significant. So that would have 2 significant figures. That second example there, that 122.35 meters, is going to have 5 significant figures. In our next example, we have a 0 between non-zero digits. So again, this is our sandwich situation. So the 2 and the 5 in that 205 degrees Celsius, those are both significant because they're non-zero digits. The 0 is sandwiched, and so that is also significant. So that would have 3 significant figures. Whereas at 5.008 kilograms, those 2 zeros are sandwiched, and we have 4 significant figures. A 0 at the end of a decimal number, those digits are significant. So in that 50 with a decimal place afterwards, that has 2 significant figures. If we were to take that decimal point away and just have it written as 50 liters with no decimal place, that would only have 1 significant digit. That's where some confusion might creep in. In that 16.00 milliliters, those zeros are trailing after the decimal place, and so they are significant, meaning that that has 4 significant figures. Whenever you have something written in scientific notation, every digit in the coefficient number is significant. And so we're going to talk a little bit more about scientific notation, but in scientific notation, you have coefficient times 10 to some power. And so in this case, the 4.8 is our coefficient, and so that determines the number of significant figures. So there would be 2 in that example, and in 5.70 times 10 to the negative third, there would be 3 significant figures. On the other hand, if we have a 0 at the beginning of a decimal number, as is the case with these 2, those are not significant, and so in this example, only the 4 is significant, and in this example right here, the 7 and the 5 are significant numbers. If it's used as a placeholder in a large number without a decimal point, so again, there's no decimal point here, so none of these trailing zeros are significant. So this would have 2 and this would have 3. And so feel free to kind of work through those and let me know if you end up with any questions regarding that. All right, so what we're going to do here is go over a few examples of significant figures. And so let's start out with, say, 26.3. So when we're looking at this number 26.3, the first thing that we need to remember is that all non-zero digits are significant. And so all we have to do here is say 1, 2, 3. This has 3 sig figs. You might see significant figures written as sig figs. That's pretty common. If we have something like, I don't know, 26.049, you can see that this 0 right here is sandwiched in between these two non-zero numbers, which means that that 0 is significant. And so if we count 1, 2, 3, 4, 5, this has 5 sig figs. If we look at something like 205.9700, again, we're focusing on those non-zero digits because we're focusing on the zeros because the non-zero digits are automatically significant. So if we look at this first 0, it's sandwiched in between the 2 and the 5, and so that would make that digit significant. And these two zeros right here are trailing, but they're trailing after the decimal point. And so those are also significant. So we can count 1, 2, 3, 4, 5, 6, 7 in that number. Let's see. If we have 0.00790, all of these right here are zeros that precede are non-zero digits, and so really those are just placeholders, and so we can say those are not significant. However, this 0 right here is trailing after the decimal point, and so we would say that that is significant, and so this has 3 significant figures. Let's see. If I want to look at, I don't know, 76,000. These zeros right here are trailing zeros before the decimal place, and those are not significant, and so this would have 2 significant figures. When we have significant figures, we need to look at some rules when it comes to adding, subtracting, multiplying, and dividing numbers. So you have a few different rules. When it comes to addition and subtraction, your answer is going to have the same number of decimal places as the original number with the fewest decimal places. So really we're going with significant decimal places when we're doing addition and subtraction. And so in this first example where you have 10.11 kilograms minus 3.6, if we count significant decimal places for each of those, 10.11 has 2 significant decimal places where 3.6 kilograms only has 1. And so our answer in this case would be allowed one decimal place. And so we would go ahead and do our subtraction problem. We know we're only allowed one decimal place, and so our final answer would be that 6.5 kilograms. When we're multiplying and dividing, on the other hand, you're going to go with the fewest number of significant figures in your whole original numbers. And so if we look at this problem where we're looking at 351.2 miles in 5.5 hours, if we want to calculate what that speed is by coming up with miles per hour, we need to count how many significant figures are in each of these numbers. So our 351.2 miles has 4 significant figures, 5.5 hours has 2 significant figures, and so what that means is our answer is only going to be allowed to have 2 significant figures. So if I go ahead and do that division, I get this number right here. But again, when I think about how precise are my instruments, they're not going to measure miles out to this many decimal places, right? And so our answer also is not going to measure out to that many decimal places because those are not significant digits at that point. And so what we would do then is round our answer to have 2 significant figures. And so this would actually be 64 miles per hour. You also need to make sure when you do this that you round appropriately. And so the way that you do that is you looked to the first digit to be dropped, if that digit to be dropped, if that first digit to be dropped is between 0 and 4, then it's going to stay the same. If it's between 5 and 9, you're going to round that last digit to be retained up by 1. So in this case, we have our 63.854545, our last allowed digit. So this 3 right here would be our last significant digit that we would be allowed, because we're only allowed 2. And so we look to that 8 to decide, are we going to keep it the same or round up? Because that 8 is between 5 and 9, that's going to make this round up to 64 miles per hour. So with 8.4234, if I want to round that to 3 significant figures, that means my 8 is significant, my 4 is significant, and then this 2, this place right here is going to be my last digit that I'm allowed in this column, where I'm allowed 3 significant figures. So we're going to check here, and we're going to say, okay, this is the digit to be retained. This 3 means that that 2 is going to stay the same. On the other hand, if I'm rounding to 2 significant digits, this 8 is my first, this would be my second, and looking to the 2, that is also going to stay the same. So it would be 8.42 and 8.4. When I'm looking at this 14.78, I retain the 1, I retain the 4. This 7, if I'm going to 3 significant figures, is my last retained digit. So I need to look to the right of that, which is an 8. That 8 is going to cause this to be rounded up to 14.8. If I want to round that to 2 significant figures, the 1 is retained. This would be my second digit retained. I have to look to that 7, which is going to make that round up to 15. And then if I do the same in the last case, I'm going to end up with 3,260. Or you can put that into scientific notation to 3.26 times 10 to the third, or 3,300, or 3.3 times 10 to the third. Okay, scientific notation. So scientific notation is just a number written as some coefficient, which is always a number between 1 and 10, times 10 to an exponent, where the exponent is any positive or negative whole number. So we're not talking about 0.5s or anything like that. It's always going to be a whole number, and it can be positive or negative. And remember that coefficient is always going to be between 1 and 10. So when you're converting a standard number to scientific notation, the first thing you need to do is move the decimal point to give you that number between 1 and 10. From there, you're going to multiply the result by 10 to whatever power, and that power is going to be determined by how many decimal places you moved, how many places the decimal was moved, and if you moved it to the left or if you moved it to the right. And so let's go through these couple examples, and then we'll kind of proceed with some other ones as well. But when we're looking at 2,500, so right now the decimal place is going to come at the end. So right here would be where the decimal place is. Now, in order to get a whole number between 1 and 10, I need to move the decimal place until it's between those numbers, that 2 and the 5. And so my coefficient is then going to be 2.5. And then I count how many decimal places I moved it. So if my decimal started here, I moved it 1, 2, 3. So this is going to be 2.5 times 10 to the third. 3 because I moved my decimal 3 places, and it's positive 3 because I moved it to the left. However, the way that I like to remember this is, as far as positive or negative, is did I start with a big number or a small number? So 2,500 is a big number, right? Meaning it's more than 1. You'll notice that when I'm doing scientific notation and my exponent is negative, that number, that original number in standard notation, is going to be less than 1. So 2,500 comparatively is a big number. If it's a big number, I know my exponent is going to be positive. Whereas in this point 036, we can see that this is a small number and we end up with a negative exponent. So that's kind of how I like to keep it straight in my head. But with this 0.036, I would say, okay, I move it 2 spaces to the right, and so that's where this -2 comes from, and I had to move it the 2 spaces to get it between a number between 1 and 10. Okay, so we have some numbers set up here that we are going to convert into scientific notation. So the first thing I need to do is say, okay, my decimal place is starting out right here, and now I need to move it, right? And so I'm going to move this, choop, 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 until I get a number that is between 1 and 10. So I'm always going to have one non-zero digit followed by whatever other digits I have. And so when I move that, my number portion, my coefficient, is going to be 4.639. And then it's always times 10 to some power. The way I determine what my power is how many places I moved it. So if I count, I moved it 1, 2, 3, 4 places. And then you can either say, okay, I moved it to the right, or you can say, this is a very small number. Because it's a very small number, because I moved the decimal to the right, this is going to be to the -4th power. In my next example, I'm going to follow that same pattern. So my decimal place starts here. I move it to get a number between 1 and 10. So I have 3.21 times 10. I moved it to the right, or I can say it's a very small number, and so my exponent is going to be negative, and I moved it 1, 2, 3 places. So it's going to be to the -3rd power. In the next case, there's no decimal place written as is, and so the decimal place is actually right there. And so what I would do then is say, okay, I need to move it 1, 2, 3, 4, 5, 6. Now I have a number that's between 1 and 10, so I can write 2.4 times 10. I moved it to the left, or I can think, okay, it's a really big number, and so it's going to be a positive exponent, and I moved it 1, 2, 3, 4, 5, 6 places. So 2.4 times 10 to the 6th. In that next number, similarly, that decimal place would be there. I would say 1, 2, 3, 4, 5, 6, 7, and 8. So it would be 2.606 times 10 to the +8. 8 positive because it's a big number, or because I moved it to the left. Either way of thinking works. We can also convert a number that's in scientific notation to a number in standard notation. And so, again, we're going to ask ourselves the same types of questions, but we are going to kind of think about our exponents in the opposite way. And so in this case, we have 2.80 times 10 to the 2. And so I know because it is a positive exponent, it's going to be a big number, meaning more than 1. And so I know I need to move my decimal place to the right, and I know I need to move it 2 places because this integer is 2. And so I just take this decimal place, 1, 2, and it would be 280. On the other hand, when the exponent is negative, I'm going to move that decimal point to the left instead of to the right. And so I would take this decimal point and I would say whoop, whoop, and my new decimal point would be here, and I fill in any space with zeros. And so you can see I had to add a 0 here to make that a correct statement. Okay, so when we're doing scientific notation into standard notation, we need to take that same thinking and but kind of in reverse. So here we have our 1.39, and we know it's a -4 exponent. And so that's going to tell us that this number is very small, meaning it's less than 1. So when I move my decimal place, I know I'm going to need to move it to the left to make a small number, and I'm going to move it 4 places because of that 4. And so I go 1, 2, 3, 4. That's where my new decimal point goes, and I know I need to fill in those spaces with zeros. And so this is going to be 0.000139. 9. You can see why we use scientific notation, because while these exponents are things like -4 and -3, when we get into things like talking about the mole, we'll have 6.02 times 10 to the 23rd. And so you can see how, that gets a little bit time consuming to write out 23 zeros every time. So scientific notation is very useful in chemistry, where we're generally talking about things that are very, very small. So in this next example, we have 1.02 times 10 to the -3rd. And so I always start again by rewriting out that number. Then I say to myself, okay, it's negative, so I know that this is a very small number, or I need to move my decimal place to the left. And so I would come here, I would say 1, 2, and 3, add that new decimal point, and I know I need to fill in those spaces with zeros. So this would be 0.00102. In this case, we have 4.7 times 10 to the 3rd. Again, I'm going to start by writing out that number. I'm going to say 3 is a positive number. This is going to be a number that's bigger than 1. So I'm going to move my decimal to the right. And I'm going to say 1, 2, 3. I add a 0 and a 0, and this is 4,700. Now, when it comes to converting these into scientific notation, you'll have to pay attention to significant figures and how many you're allowed. That will determine things like if we need to add zeros to the end of these numbers, or do I need to add a decimal with some zeros. That is all going to be based on the number of significant figures that you're allowed. The important thing when it comes to measurements is that measurements are composed of both a number and a unit. A number is meaningless without the units, and so when you're talking about things like aspirin dosage, you can say it's 325, but 325 milligrams is a lot different than 325 pounds, and so it's really important that you are always including your units, and I'm going to say this so many times throughout the semester, always include your units. It makes your life and my life a lot easier. So in science, we use the metric system. The metric system is a really nice system. It's based off of the power of 10, and so everything is nice and neat, which is much different than our system of measurement, which is really all over the place. And so we use that metric system when we're in science fields. So we have base units that correspond to various types of measurements. So in chemistry, we might want to measure length, and we would use the meter as our base unit. When we're talking about mass, we talk about grams. Volume, we're talking about liters. In time, we're talking about seconds. Those are the base metric units. From there, we have prefixes that correspond to a power of 10. So the prefix is going to indicate if the unit is larger or smaller than the base unit, as well as by how much. And so these are some common prefixes that are used in the metric system. So giga, mega, you might be used to seeing those when we're talking about like technology. So your computer might be so many gigabytes. In that case, byte would be the base unit that we're discussing. More common in chemistry is the kilo. So that would be like the kilometer, the kilogram. That means the 1,000, so 10 to the 3rd. And what that means is that in a kilometer, there's 1,000 meters. In a kilogram, there's 1,000 grams. So kilo means 10 to the 3rd. Other common ones are centi and milli. So centi is 10 to the -2, so that means there's 100 centimeters in a meter. Milli is 10 to the -3, so that's kind of the flip side of the coin from kilo. And so what that means is that there's 1,000 millimeters in a meter. Micro and nano are also pretty common units in chemistry, but as far as which units that I would have you memorize, please memorize kilo, centi, milli, micro, and nano. Those are the ones that I would like to have you memorize. So when it comes to length, like I said, the base unit of length is the meter. 1 kilometer is 1,000 meters. 1 millimeter is 0.001 meters. But the other way to say that is that 1 meter is 1,000 millimeters. I always like to keep the 1 with a bigger unit when I'm doing conversions. And as we start to do more and more conversions, you'll see what I mean by that. And so, again, when we're looking at centimeters, 1 centimeter is 0.01 meters. How I like to think of that instead is that 1 meter has 100 centimeters. Mass is just the amount of matter in an object. Remember, I matter, you matter, we all matter. Everything matters. And so mass is just a measure of how much of matter is in an object. Weight is... it corresponds to that, but weight has to do with gravity. And so when we're talking about weight is going to be different whether you're talking about weight on the moon or on Earth or on Mars, where mass is just a unit, it's how much matter there is. So it's going to be the same regardless of where you're located. So the base unit of mass is the gram. You can see that these prefixes, so here kilo and milli, those are the same whether you're talking about mass or whether you're talking about any other, so length in the case of what we just talked about. So 1 kilogram is 1,000 grams, just like 1 kilometer is 1,000 meters. So that pattern is the same. On the flip side of that, the milligram is 0.001 grams, or you can think about it as 1 gram is 1,000 milligrams. When it comes to volume, you're going to, again, see the same thing here. Our base unit is the liter, kiloliter, although you don't hear that as often. That is a real unit that's used, and it means the same thing as when you're talking about grams or meters, where that kilo is 1,000. You can also measure volume by doing length times width times height, and actually 1 centimeter cubed is the equivalent of 1 milliliter, so that's a conversion that you might find useful. These right here, these are equalities. These are definitions that take us from one system of measurement to another. So the one conversion factor that I would have you memorize on this list is 1 inch is 2.54 centimeters. Any of these other conversions, if you needed them on an exam or on homework or in the lab, I would provide these conversion factors for you. So when you solve problems using conversion factors, you're going to take your original quantity, you're going to multiply it by your conversion factor to get a desired quantity. So our conversion factors can be written as equalities, and to use them you can write them as fractions. So in this case, the conversion that we want to look at, we're going to use this 2.2 pounds is equivalent to 1 kilogram. This right here is an equality, and we can write those as fractions that we can then use to multiply by our original quantity to get our desired quantity. And so depending on what we're looking for, we might need this first conversion factor, or we might need the inverse of it and need the second conversion factor. It really depends on where you're starting and where you're going, and you're going to hear me talk about this pattern quite a bit as well. And so if we want to convert 130 pounds into kilograms, the first thing that we need to do is figure out where we're starting and where we want to go. So you always want to write that out. So I would write down, I'm given 130 pounds. I know I need to multiply it by some conversion factor, and I want my answer to be in kilograms. From there, I need to figure out what conversion factor do I need to cancel out my units. And so what that means is I have a unit right here in pounds. So that pounds is in the numerator right now. If I want to cancel out a unit in the next step, it needs to go in the denominator. And so if I use this conversion factor, I would have pounds in the numerator here and here. So this conversion factor does not work for me. In this case, I want this conversion factor because pounds is on the top here. I want it on the bottom in my next step to cancel out, and I'm left with that unit that I want. once you do your problem, you have to look back to your original problem to see what you were given and how many significant figures you were allowed. And so in this case, again, we're using this bottom conversion factor. Okay, so here pounds would cancel out. I was originally given a quantity that had 2 significant figures. My conversion factor has 3 significant figures, so my answer is only allowed 2 significant figures. So that's where this answer with 2 significant figures comes from. So when I'm doing that problem solving process, I'm going to analyze my problem, I'm going to identify what's given, I'm going to look at what's needed, then I'm going to create a plan that kind of gets me to where I want to be, and I'm going to identify 1 or more conversion factors to cancel the units, and then set up my calculation from there. These are the conversion factors that I'm provided, and the problem reads, it's Halloween and you are handing out candy. Over the course of the night, you hear 46 bams. How many bangs did you hear? And so this is just kind of a nonsense problem to get you used to the pattern before we start to put units into these things. It kind of helps to learn that process without trying to kind of insert what you already know to really get at what the process is. And so the first thing that I do when I look at one of these problems is to figure out what do they give me and where do I want to go. So in the problem it tells me I hear 46 bams. And then I want to know how many bangs. And so what I'm going to do is I'm going to set this up with what they give me. So they give me the 46 bams, and I use something that's called the railroad method. And so what that means is I just I write it in one big line with kind of these vertical lines separating each of my kind of multiplication or division steps, and then I at the end will multiply what's on the top and what's on the bottom. And so you're going to hear this pattern quite a bit as I go through. Sorry, we don't want to know bams, we want to know bangs. But you're going to notice that I am going to be using the same patterns of speaking as I go through these problems. And so what I say is I start with 46 bams. Do I want bams as my unit when I end? No. And because I don't want that as my units at the end, in my next step it needs to go on the bottom. And so let's come over here and we're going to talk about why does it need to go on the bottom. If I have a fraction that's say 5 over 5, okay, I can cancel these out, right? And that equals 1. If I have something that's say 25 over 5, I can say that that 25 is equivalent to 5 times 5 over 5. Those cancel and I'm left with 5, right? And so you can see how numbers can cancel from numerator to denominator. The same thing is true with units. If I have something that's grams over grams, those units cancel and it's left with 1. And so when I'm doing a problem like this, I can say, okay, I don't want bams, and it's in the numerator now, so in my next step it has to go in the denominator. Then I say, okay, where do I want to get to? I want to get to bangs. Do I have a conversion factor that's going to get me directly from bams into bangs? And the answer is yes. So I can put bams on the bottom and bangs on top, and if I look right here at this conversion factor, I see that 1 bam is equal to 3 bangs. And so I can say 1 bam is equal to 3 bangs, and I can go ahead and do that math. And 46 times 3, of course I don't have a calculator. And of course I find a calculator and the battery is dead. And so I can do or 46 times 3 is going to give me 138. 138 bangs. But I have to go back to my original problem. I have to say, okay, I was given two significant figures. My conversion factor, those are exact values. That's a definition. And so I'm allowed two significant figures in my answer. And so my answer would actually be 140 bangs. This same process can be repeated for as many conversions as you have to use, as long as each individual step makes sense, meaning you're not breaking any rules, you're not giving an equality that's not true. You can repeat this process for as many times as you needed to get the right units, again, as long as each of those individual steps is a true statement. And so we're going to look at this problem. We're going to use those same conversion factors. A person is walking their dogs and hears 12 clashes along the way. How many bams did the person hear? Okay, so again, the problem reads, a person is walking their dog and hears 12 clashes along the way. How many bams did the person hear? So I would start again by saying, okay, we have 12 clashes. Go ahead and put in my railroad kind of chart to get me started, and I know that at the end I want to end up with bams. So the first thing I'm going to say is I'm in clashes. I don't want to be in clashes, and so in order to get rid of it, it needs to go in the bottom. Do I have a piece of information that gets me directly from clashes to bams where I want to be? The answer to that is no, but I can get from clashes to bops using the conversion factors that I have. So it's 4 clashes to 1 bop based on my conversion factor right here. So when I do that, those clashes cancel out. And so now I'm in bops. Do I want bops in my answer? No, I don't want bops in my answer. I want bams. And so I go ahead and put my bops in the denominator to get rid of it. And I say, okay, do I have a conversion factor that gets me directly from bops to bams? And if I look at the conversion factors I'm given, I don't have that. But I can get from bops to bangs. And that is a 2 bangs to 4 bops conversion. And I can go ahead and cancel out my bops. Now, I'm in bangs. I don't want bangs, I want bams. So in my next step, bangs has to go on the bottom. And I can go from bangs to bams. Using this conversion factor where 1 bam is equal to 3 bangs. The bangs cancel out, and I'm left in bams, which is what I want. Now when I go to put this in my calculator, what I'm going to do is I'm going to multiply everything on the top, and I'm going to divide everything on the bottom. And so when I go to put this into my calculator, I would say 12 times 2 divided by 4 divided by 4 divided by 3, and I'm going to get 0.5 bams. That's a terrible color, so we'll switch that up, and it'll be 0.5 bams. Now the thing is I need to go back to my original problem, and in my original problem I'm given 12 clashes, and so 12 clashes, that has 2 significant figures. The others are definitions, and so they don't contribute to the number of significant figures. And so my answer I know needs to have 2 significant figures, and so for this I would put 0. I would put 0.50 bams. Again, that 0, this 0 right here, is trailing after the decimal point, and so it is significant. All right, so the last topic that I want to talk about is density and specific gravity. So density is a physical property. So again, it's something that is a property of a substance that you don't have to change the chemical makeup to observe it. It's just something that's a physical property related to the substance. And you can define density as mass divided by volume. And you can also use it as a conversion factor, which is really nice. So density is grams per milliliter. You can use the inverse of it as milliliters over grams. And so you can use that to your advantage as you're going through some conversion type things. So an example of this is if the density of acetic acid is 1.05 grams per milliliter, what is the volume of 5 grams of acetic acid? There's a couple of different ways that you can think about this. One is to think about it as a formula, so density equals mass divided by volume. You can certainly rearrange that equation to solve for volume. So density equals mass divided by volume. So volume is going to be equal to density divided by mass. Or you can go ahead and use that railroad method again and use that density as a conversion factor. And so I know that if I start with 5 grams of the original quantity, I need to use a conversion factor where I have grams in the denominator in order to cancel out. And so I'm going to use this second conversion factor to cancel out my grams and end up with an answer in milliliters. And so when I do that, I can set up this 5 grams times the conversion factor 1 milliliter over 1.05 grams. Those grams cancel out, and I am left with this on my calculator. Now, this is a lot of decimal places, right? I don't go into the lab and get a graduated cylinder that's going to measure out milliliters to this many decimal places, right? And so this is where that significant figures idea comes into place. I was originally given a quantity that has 2 significant figures, and so what that means is my answer also has to have 2 significant figures. And so I'd say, okay, I have 4 point, this is going to be that second digit, so this is the retained digit. I'm going to look to the right of that. This 6 is going to make this round up to 4.8 milliliters. Specific gravity is it really is a quantity that compares density of a substance with the density of water at the same temperature. So density is something that is temperature dependent. As we know, when we think about the density of water versus the density of ice, we know that ice is actually less dense than water, which is why your ice cubes are going to float and things like that. And so specific gravity is just a measure of the ratio between the density of a substance and the density of water at that same temperature. Because the units in the denominator, grams per milliliter, are going to be the same as the units in the denominator, grams per milliliter, those cancel out, and specific gravity is equal to its density but is unitless. And that's all I have for Chapter 1. I am going to go over it in class as well so that we can kind of get on the same page as a class. But let's work together so that we can make sure that we are all on the same page and we're all, successful in the class. So ask questions, refer back to this, etc., etc.